What is statistical thinking? What does industry need? And can we teach it better in our universities? Mia Stevens from Jump defines statistical thinking as managing the variation that occurs in engineering processes. Her company surveyed industry experts and academics on the skills gap between what's taught and what companies need. The responses revealed that educators typically teach statistical theory ungrounded in industry problem-first methodologies, and that students are better off interacting with data assisted by visual explorations. To close this skills gap, Jump has developed a tool called Design of Experiments, which may be accessed through their free online course STIPS.
Welcome to the European Engineering Educators podcast by SEFI, the European Society for Engineering Education. We're a non-profit international organisation active since 1973 and the largest European network of engineering educators. Our mission is to develop and improve engineering education and strengthen its image in society.
So welcome to this episode. I'm Neil Cook.
And I'm Natalie Wint.
So today we'll discuss what statistical thinking is and the support that Jump is providing to engineering educators to better teach it. I sometimes take statistical thinking for granted, and I don't always recognise that many of the students are not going to go on to academic research and won't have gone through the rigours of peer review process, which has really forged my statistical skills. Do us as engineering educators teach what industry wants?
So yeah, I think it's interesting you picked up on that, Neil. I mean, in some of the industrial advisory boards that we have at Swansea, employers are sort of increasingly saying that they want students to be able to manage big data sets. But I often find with my PhD students who are starting that they quite often struggle with this sort of statistical side of data collection during research. So I do think there is some gap there. Hi Mia, welcome.
Thank you. Thanks for having me.
So Mia Stevens is a Jump Advisory Product Manager. Prior to joining Jump, she was an Adjunct Professor of Statistics at the University of New Hampshire and a founding member, statistical trainer and consultant with the North Haven Group. She has taught and consulted within a variety of industries and is an author of 4 books, including Visual Six Sigma, Making Data Analysis Lean. She is also the lead developer and instructor of the free online course Statistical Thinking for Industry Problem Solving. Mia, I'm really looking forward to hearing your mixed perspectives from both industry and academia.
Hi Mia.
Hi. Thanks for that nice introduction.
You're welcome. So Jump is a corporate partner of SEFI, and it produces interactive software for desktop statistics. And I looked at the history of it, and it was formed way back in 1989, sort of the advent of computers, desktop computers with graphical user interfaces like the Apple Macintosh. And, one of Jump's early missions was to produce a graph for every statistic. Could you tell us a bit about Jump today and how it's helping engineering educators?
Sure. Yeah, so Jump started as a subdivision of SAS. In fact, our co-founders, John Saul, was one of the original developers of SAS. And it was designed so that engineers and scientists who had data could make better decisions with that data. And at the time, the Apple Macintosh had just come out. It was a nice little desktop computer. So we wanted something that we could use on a desktop rather than having to use a mainframe system. So the whole Jump interface is based on being interactive, being graphical, and this premise of a graph for every statistic still holds. So even for very advanced methods, advanced statistical methods, advanced modeling methods, there's always a graph, and all of the graphs are interactive and they're linked directly back to the data. So Jump facilitates exploration. It facilitates discovery. So our name, Jump Discovery Software, is all about discovering the message that's in the data. What is our data trying to tell us?
Before we start on your work in this area, could you give us a quick summary of what we mean by statistical thinking and why you think it's important to teach?
Sure, good question. Yeah, so statistical thinking is about understanding that all work occurs in processes. So everything we do, everything we create, everything we make occurs in a process. There are a series of steps. And within every process and within every process step, there's variation. So engineers create things, they make things, they design things. But everything we create and we make and we design has random variation. So in order to make improvements, to optimize a process, to make things better, we have to understand this variation. And that's really what statistical thinking is all about. And so statistical thinking kind of relies on having some fundamental knowledge of how to work with variation and how to make decisions in light of variation.
So this word variation is key to statistical thinking, and explaining variance in all forms of data can be assisted by visual presentation.
Sure, visual presentation. Visual presentation can give you insights into what might be happening. If you measure something, for example, if you step on the scale in the morning and you weigh yourself, you probably weigh close to what you think you should weigh. If you step off and you step on again, do you get the exact same measurement, or is it slightly different? If you weigh yourself later in the day, is it the same or is it different? It's usually a little bit different. So this is variation. Sometimes we get pretty close to where we think we're at, but from one measurement to another, things might be a little bit different. So things aren't always exactly what we think they should be. So variation is this unexpected noise. And what we're often trying to do as engineers is detect the signal through all this noise.
JUMP has been very much in the intersection between companies across the world and academia, and surveyed a large number of these companies on the skills gap between what we're teaching in engineering schools and what they need. Could you tell us more about this survey and how it came about?
Sure. So the survey was done with the end goal of developing a course in statistical thinking. In my work, when I early in my career at JUMP, I worked with the academic group, and the academic group works with professors teaching statistics across the world. This group is integrated with industry, local industry in different countries. And one of the messages that we heard was that new engineers coming in don't really have a good background in statistics. So we decided to develop a course, and the first step in developing this course to help offload some of the statistical education was to conduct a survey. And in the survey, we asked JUMP users and experts and academics in countries around the world things like, what kinds of tools are engineers using in practice? What are the gaps? What are the things that they struggle with? When you're working with data, particularly big data, what are the challenges? So we learned a lot about the different methods that are most commonly used. Some of this was confirming what we already suspected, but we also learned a lot. Like, we learned that data preparation continues to be a problem or a challenge. How do we get data in to a statistical software package where we can analyze it? How do we better understand the data? How do we understand the data that we need? So the survey was really insightful in terms of, what are we teaching in industry in an applied statistical course versus what do we need when we actually get out into the field?
When you spoke to industry, you talked about there were tools that they were using, and they talked to you about the challenges that they had in that data and how those tools were helping them to address those challenges. When you compared that to what was going on in the academic space, what would you say was the biggest deficiency within the engineering schools, or the difference? What were they focusing on much more than industry, and vice versa?
Yeah, I'd say that typically what we would see at the university level is statistics taught in a very theoretical manner. So I taught industrial statistics for engineers at the university, and the requirement was that it was a calculus-based course. Engineers get a lot of calculus, they get a lot of theory, but to be effective in using statistics, it really needs to be practical and applied. So one of the things we saw, or I saw, was a disconnect between the way that we're teaching statistics at the university level and what students actually need when they get out into the field. To be effective in applying statistics, it's really practical, it's really hands-on. You look at your data, you see your data, you visualize with your data, you interact with your data. But this typically isn't what's taught in the university. What we also saw a lot of was that, engineering programs are very dense. I mean, there are a lot of courses. The course load is very heavy. So there's a lack of appreciation for how important it is to be able to work with data, to be able to make good decisions with data, to be able to design experiments. So the curriculum, most programs require maybe one statistics course. Some require an engineering course, or a design of experiments course. Most are limited to one, and most of the time it's very theoretical. The course that I taught was very applied. The final exam was actually a project where students had to design an experiment and write up their results and then share the results with the group. When you're working with statistics, it's not a math course. It should be applied, because fundamentally we need to be able to make better decisions with the data that we're faced with.
So I'm assuming then that some of the sort of survey responses was what helped inform your sort of approach. So I know you developed your approach to teaching statistical thinking on the Visual Six Sigma process. And in fact, you co-authored a book, Visual Six Sigma, Making Data Analysis Lean. So how exactly is this related to Six Sigma?
So the book came out several years ago, and the survey was done about 4 years ago. So the survey came much later. My background in consulting was teaching Six Sigma, teaching statistical methods in industry. And Six Sigma is it's a practical approach to problem solving that's process oriented, and it's also problem oriented. Visual Six Sigma really takes this Six Sigma thinking a step further and is based on this premise that you can learn a lot about what's going on in your process by using exploratory data tools. So you don't need necessarily heavy statistical tools like hypothesis testing and statistical modeling to be able to get insights into what's going on in your process or what might be causing failures. So the Visual Six Sigma book took this thinking of Six Sigma a step further to make it very practical. When we're working with data, start with exploring your data. So this idea of statistics as detective. You're investigating, you're exploring, you're trying to see what kinds of insights you can gain from looking at your data. And this then can lead you to designing an experiment or to studying parts of the process much more closely.
And I'm assuming that this approach is a lot more accessible for students and even engineering educators. Would you say that's true?
I would definitely say that's true. In the old days of teaching Six Sigma, I taught Six Sigma about 20 years ago. There was a heavy reliance on classical methods, inference, so hypothesis testing, regression analysis. And it takes a lot to really master those skills. But if you take a step back and you think, what is the process that I'm trying to improve? And you collect data on that process, and then you use simple tools for visualizing those data, like a run chart or a histogram or a box plot, just very, very basic tools. Oftentimes you see signals. You see things that pop out where you say, wow, what is that? What's going on? And this can lead you to further investigation. So statistical tools like statistical modeling, some of the more advanced tools, are very powerful. Design of experiments is probably the most powerful tool in any toolkit. Helps you to make statements of cause and effect. But to get there, and this is really a premise of the Visual Six Sigma book, you start by looking at your data, by asking questions, by investigating, by exploring.
What you're saying, Mia, is that universities tended to teach statistics in a theoretical manner compared to what was needed in industry from that skills gap. And you talked about the curriculum itself being limited in terms of how it was enabling statistics to be taught. Why do you think that is? Why do you think that statistics isn't taught more like what industry would like, and we still maintain this theoretical base and don't look at these process-oriented Six Sigma type approaches?
Well, I think there are many contributing factors. I think one is that statistical skills aren't fully appreciated. When we've worked with engineers in the field, part of my work in the consulting group was to provide customized statistical training for engineers and scientists. And we'd always start off by asking, how many of you took a statistics course when you were at the university? And there'd usually be grumbling. People would say, oh, I took it. It was the worst course I ever had. I don't remember a thing.
Yeah.
But some would say, I wish I paid attention.
Yeah.
So sometimes the way we're teaching it, we're not teaching it to engage students to get excited about using statistics. And to me, statistics is fascinating because it's all about learning. It's all about knowledge. Part of the problem also is that students at that point in their career don't really have a perspective that they need statistics. So a lot of the engineers we'd work with, when they'd say things like, I wish I'd paid attention, I really need these skills, they didn't know that when they were in the university. We were taught that the world works according to first principles. But in reality, there's variation in everything we do. And making that connection is very difficult until you're in the field, until you're trying to solve problems and things aren't quite working the way you think they're supposed to work.
So can you tell us a bit about your experience of teaching engineering statistics when you were at University of New Hampshire and the sort of reaction that you were getting to trying to use this approach with students?
So I tried to make the course as applied as possible. So it mirrored the way we would teach engineers when we were teaching Six Sigma. So this thinking about, you're not just learning what a p-value is. You're not just learning what a t-test is. You're not computing numbers and values, and you're not spending all your time working on formulas. I tried to set the course up so that there were a lot of hands-on exercises. So we used wooden catapults, which is pretty common for teaching statistics in industry. We used wooden catapults to design experiments. We had in-class exercises where the groups would collect data and then they'd analyze those data. And part of the challenge of statistics is, the language can be very difficult. So if it's taught in a way where people are more confident in using the methods and then saying, this is what I learned, then you're giving them those skills as well. So statistics is about picking the right tool. It's about asking questions, and it's about being able to interpret what the results are telling you. And that's typically not taught in most university courses. The topics also were different in the course that I taught. Most introductory statistics courses, I teach descriptive statistics, basic data analysis, but they go pretty quickly into the heavier topics. So I focused a little bit more on interactivity. I focused a little bit more on design of experiments. And some of the quality tools that are really, really important for engineers are things like statistical process control. That's understanding the behavior in your process over time. Measurement systems analysis. Is my measurement system capable of producing reliable results? And capability analysis. is my process capable of meeting specifications? So I focused a little bit more on the quality related tools that are very popular in industry. And of course, design of experiments. And design of experiments, if there's one tool that an engineering student needs to learn, or technique an engineering student needs, is design of experiments.
So we have the skills gap defined as, perhaps in universities we are focusing in engineering still very much on applied science. Mm-hmm. And we have students who then go into the real world where the science doesn't take precedence to just trying to explain variance and handle variance. And you talked about the idea of design of experiments as being the core skill in bridging that gap. Could you give us an example of a design of experiment then? If somebody wants to think, well, I'll put a design of experiment now into my statistics course, which one would you say would be a really good starting point?
Oh, that's a tough question. I mean, I think a starting point is to talk about what designed experiments or statistically designed experiment is. Oftentimes we're studying a process, and if you think about creating a map of that process where there are a series of steps, and at each step there are things that go on within that step, and there might be other inputs like raw materials that go into that step.
Yeah. And
these steps are all connected, and each step produces something. So we've got inputs, we've got outputs, we've got these process steps, we've got different parameters, and at the end we're producing something. And maybe we're measuring the yield, or maybe we're measuring some sort of characteristic like breaking strength. And maybe we design this process, and when we measure this characteristic, it's not where we want it to be. So the breaking strength it's not strong enough, or the yields are too low. So how do you look at this big picture, right, the entire process with all of the inputs and all the outputs, to try to improve the breaking strength? Well, that's where a tool like design of experiments comes in. You might have data that you've collected where you know what the values were when you're running the process, but oftentimes we're not collecting the right data. So in a designed experiment, you can study different parameters at different steps, and you systematically manipulate the settings to study what happens to your outputs that you're interested in. And you design this experiment in a way that it has some optimal statistical characteristics. So basically, when I've made this change and that change, I know exactly what's going to happen to the response. So you develop this understanding of cause and effect. So design experiments, there are a lot of different types of experiments based on what it is you want to learn. If I've got a lot of factors and I don't know which ones are important, I might do what's called a screening experiment. If I have a pretty good understanding that this subset, maybe I've got 4 or 5 or 6 factors, are really, really important, and they work in a non-linear fashion, then I might want what's called a response surface design. So there are full semester courses in design experiments, and I think what's most important for engineering students, if they could take just one course, right, is just to get a basic understanding of the value and the importance of design experiments. I would do this in my Six Sigma training, where we would introduce the topic, and then we would use catapults in this example, and we said, go design this experiment, and then we are going to give you a target that you have to hit based on your findings. I would do the same thing in the university course. So I think more so than having a deep theoretical understanding of design of experiments, understanding the value of it and understanding the basic language and terminology of design experiments, I think is really critical. In JUMP, we try to make it easier. We have what's called a custom designer, and the custom designer, allows you to easily say, these are the things that I want to study, and then it gives you options. It helps you to pick the design that makes the most sense.
So, following your teaching Visual Six Sigma, your most sort of recent work is as lead developer of the course Statistical Thinking for Industrial Problem Solving. Would you be able to tell us a bit about that? Like who's it aimed at, the sort of structure of the course and what it involves?
Sure. So the course really grew out of this work with Six Sigma and Visual Six Sigma and teaching at the university. And again, it was motivated by this gap that we saw between what we're teaching in university and the skills that students have. And the reality that most students just don't have, the opportunity to take a course to develop these fundamental skills. So the survey that we talked about earlier was developed to help guide the development of this course. So we've got commitment from JUMP, and we got resources from JUMP to develop a course, and we did research. What are the topics that we should include? How should we structure the course? So we knew that we wanted an online course that was self-paced. So in the end, we developed a course with 7 modules, and each module is basically a mini course. And within each module, there are short instructional videos that are 3 to 5 minutes. We include JUMP within the course, so students can access JUMP for free as part of the course. So we include demos to show students how to apply particular methods using data. There are questions, there are practice exercises, there's quizzes at the end of each of the modules. So the topics include really very consistent with what we would use in Six Sigma and very consistent with what I taught at the university. In fact, we leveraged a lot of those materials.
And is there any sort of prerequisites? I mean, is this just as accessible for someone who is a student as for someone who's, worked in industry for a while and would like some more skills?
It's really for anyone. We've actually had high school students take it. It's a very applied course and very practical. There is just enough theory to understand what's going on under the hood if needed. But it's really for anyone who wants to improve their statistical skills, fill in gaps. A lot of times what we would see in industry is that people were self-taught in certain topics, but they really didn't know enough to branch out. So we're getting a lot of people from industry who are taking particular modules to backfill their knowledge, backfill their skills. Some university courses are using it as a prerequisite. So, for example, we have a course that teaches predictive analytics. They're using some of the modules to get students up to speed so that they can be more effective in the course itself. So it's really for anyone, anywhere who wants to develop better skills in statistics.
So STIPS is being used in engineering schools, and people are integrating it into their existing statistics training. STIPS is also used in industry. Could you give us an example of how industry is using STIPS?
Sure, and we're actually seeing quite a bit of this. So a lot of companies, particularly in the global environment, find it very difficult to develop training programs to backfill the statistical skills that their engineers need. We're seeing a lot of companies adopt STIPS and integrate it into their internal learning management systems. So they're using JUMP, and there's a certification that goes along with it and their internal badges. And they're using this really so that they can broaden their training programs.
So over the last decade, we've heard the term big data used a lot, and I'm interested to know what JUMP and your view is of statistical thinking going forward. What's next?
So good question. So I think statistical thinking is still relevant in the world of big data. So if we recall that statistical thinking is about understanding that everything occurs within a process, all processes are connected, and that there's variation within a process. With big data, we have a lot of data that might be coming in very quickly. It might be coming from sensors. We still need to be able to make good decisions.
So this is very much the Industry 4.0 mindset.
Exactly. We have a lot of data coming in from sensors. We need to process the data. We need to make quick decisions based on what we're learning. So Industry 4.0 really just, it takes it a step further.
Mia, thank you so much for sharing your insights on statistical thinking today. To finish, I was just wondering if you'd be able to share one piece of advice with us and our listeners about how they might better teach statistical thinking in their own courses and their own institutions.
Good question. I guess I'd say that if you were to think about statistical skills, statistical knowledge, tools, probably the most important tool for an engineer is statistically designed experiments, where you are manipulating parameters to develop process knowledge and understanding about parameters, about the settings, conditions, and how to optimize. So I guess my advice would be, if you have a chance to take a course in designed experiments, take it, because you'll learn how effective designed experiments are in solving problems and in driving improvement.
So if Mia, if I wanted to access the STIPS course as an engineering educator, how would I go about doing that?
Sure, it's actually very easy. There's a link on our website. So it's a free course that can be taken by anyone. It's actually been translated to Chinese, Japanese, and Korean, and is also in Coursera.
Great, thank you. We'll make sure we share that with our listeners also. So Mia, thank you so much for taking your time to be with us today. I certainly feel myself like I've managed to learn a bit more about statistical thinking and how I might make use of it when I'm teaching engineers.
Thank you. Thanks for having me today.
Thanks, Mia. That was a really good conversation about statistical thinking. What was your key takeaway, Natalie?
I think really my key takeaway would be that students need to understand why they're doing statistics, like why they're learning about statistics, if there's a need for the sort of theory, and where they might use it in the future. So maybe linking more with industrial problems, and getting them to really understand its significance and importance. What about you, Neil?
I think my takeaway just builds on what you said in terms of the theory side. Whenever I come across a situation where I need to teach statistical theory, I think I'm going to stop myself and say, is it better that I teach it with a problem-first approach?
So I guess what you mean, Neil, is that sort of students understand what the problem is, what they're trying to find out, and then maybe they're sort of thinking about what tools they can use to solve that problem, as opposed to like learning about the tools in a sort of abstract sense.
Exactly. Thanks for listening to this episode, and we hope you've learned more about statistical thinking and maybe give STIPS a try with your course. Thanks again to our guest, Mia Stevens, from our corporate partner, Jump. I'm Neil Cook.
And I'm Natalie Wint.
Goodbye.
Bye.